We are pleased to present Module CCSO5, the fourth part of our Introduction to Contamination Control. This session will discuss equipment design and maintenance, investigations, and corrective and preventive actions, or CAPAs. Today we will closely examine the best practices for contamination control strategies. The objectives of this session will cover equipment design and maintenance, investigations, quality risk management, and CAPAs. A holistic approach to equipment design can be applied by following some basic principles. Equipment design should incorporate controls that minimize the risk of contamination. This includes features such as sealed enclosures, smooth surfaces, and automated systems which reduce human intervention. Design considerations should include validated cleaning protocols tailored to the equipment's specific challenges, which ensure through cleaning and disinfection to maintain sanitary conditions between uses. Equipment should be designed with materials and surfaces that minimize moisture retention and prevent biofilm formation, which can harbor contaminants. Whenever feasible, equipment should be designed as closed systems to reduce the risk of microbial ingress and maintain product integrity throughout processing. Equipment should be constructed from sanitary materials which are easy to clean and resistant to corrosion. Additionally, avoiding particle-generating components reduces the risk of particulate contamination in sensitive processes. Equipment should incorporate smooth surfaces that are easy to clean and disinfect, which minimizes the risk of microbial attachment and facilitate effective sanitation practices. Minimizing routine human interventions in critical areas reduces the potential for contamination. Automated or closed systems can be used for this purpose. Barrier equipment such as isolators or laminar flow hoods should be equipped with interlocks which ensure that access is controlled and that operational parameters like pressure differentials are maintained. Design considerations should prioritize ease of access for operators during aseptic assembly processes, such as ergonomic designs that facilitate efficient and safe assembly of components. Ensure the passage for pipes and utilities are effectively sealed, which minimizes the risk of microbial infiltration and maintains the integrity of the sterile environments. Incorporating drainage slopes ensure proper drainage of liquids and prevents pooling, which can harbor contaminants and facilitate effective cleaning and maintenance. Filters used in exhaust systems must meet the requirement area classification standards for cleanliness and particulate removal. Air brake filters should draw sources of air from within cleanroom environment which ensures filtered air is free from external contaminants. Electronic components should be covered with surfaces that are easy to wipe clean, which prevent accumulation of dust and facilitate routine cleaning practices without compromising electronic functionality. Design equipment with considerations for ease of storage and protection. Proper storage minimizes exposure to environmental factors that could compromise cleanliness or functionality. Implementing alarm systems for critical equipment parameters ensure prompt detection and response to deviations that could compromise equipment integrity or product quality. This approach maintains operational efficiency and prevents potential contamination events. Ongoing equipment control is vital due to factors such as biofilm formation, which can occur in surfaces over time, leading to microbial growth and contamination risks. Hence, regular monitoring and cleaning protocols are essential. Residue buildup from product and cleaning agents can accumulate on equipment surfaces, necessitating effective cleaning procedures and periodic inspections to remove residues and prevent potential contamination hazards. Wear and tear in equipment components can compromise functionality and cleanliness. Regular maintenance and replacement of worn parts ensure equipment operates reliably and maintains sterile conditions. Surface damage can create harborage sites for contaminants. Designing equipment with durable materials and conducting routine inspections prevents surface damage that could compromise cleanliness. Placement of fixed probes such as temperature or pressure sensors should be strategically determined based on risk assessments. Probes should be positioned to monitor critical parameters effectively, ensuring equipment operates within specified limits and minimizing contamination risks. Single-use systems such as bags and flow paths are widely used in manufacturing due to their ability to create closed system environment, which minimize the risk of cross-contamination between batches and eliminate the need for cleaning and sterilization, which enhances operational efficiency. Tube welders link various components of single-use systems. Proper welding ensures secure connections that maintain system integrity and prevent leaks or contamination risks during fluid transfer processes. Incorporating barrier separation technology ensures effective separation between the operators and the process environment, allowing for aseptic conditions and minimizing the risk of microbial contamination. Closed systems provide the highest level of contamination control by eliminating external exposure to the manufacturing process. Thank you for watching this introduction to this module. If you'd like to watch the remainder and get 25% off our Contamination Control Fundamental program, head over to our website at pharmalliance.ie/training-programs and use code YT25OFF. Please do it now as spaces are limited and it's expiring soon. Thank you for your time, and we'll see you on the next module.